In the title, there are 4 key concepts: Pareto distributions, image statistics, autofocusing, and automated microscopy. But since I have a little bit more time than I initially thought, I think I will say something more general and put it in a wider context. So here is an example from automated microscopy, where you have 34 different slices from a single specimen. And in automatic microscopy, you have simply a microscope that goes through thousands and millions of these specimens. And one problem is to have an autofocus method here. And I guess even if you have never worked with microscopy, you would probably say that in this region here, the images are sharp. So, no problem. Here is another example. And I took a focus sequence with 192, I think, different focus positions with a very cheap compact camera. And so this is the first position, and then there are 16 different focus positions between each of them. And you see here everything is blurred, and then it becomes a little bit sharper. Then here it becomes even more sharper, there. And now if you focus on this area here, you see that this becomes sharp. So we take the next one here, and then this one here is sharp, and then it becomes blurred again. And you see in the background here on the wall, a picture frame is coming up. So, no problem. Everybody can do this. And if you do this patchwise, you can produce an image where everything is in focus. So, some observations here. Autofocus is really easy. I mean, everybody can do it. Then from the second sequence, you saw that, or from the 2 sequences, you see that you can solve this problem easily independent of what you see. So if it's a plant, if it's a frame, or if it's a microscope image, you can do it. You don't need to know anything about who produced or how these images were produced. If it was a microscope, if it was a cheap camera or whatsoever. The next thing is it's really fast. You don't have to think about it. You look at it and say, okay, this is in focus. So, and then it's also local. So you don't look at the whole image, but you can see certain parts of the pictures are in focus, others are not. So if you think of this here in a general context, then you can certainly draw some conclusions here. So for example, this real-time business here, if you think in terms of the human visual system, this means that everything has to go really fast, which means that it has to be produced near the retina or in the first stages of the visual system. Because if it took a too long time here, then you have to send it to the cortex. The cortex has to do some processing, and then you have to do some other processing, and then you have to send a signal to your arms or to your feet. And yeah, I mean, it takes too long. So if you are in the savannah and you look at something and you have to decide if this something is a snake or if it's a piece of wood, then you better do it fast. So this has to be done very fast, and since you have to do it in our system relatively near the retina, you have only very limited processing power. So the mechanisms that you have are probably very primitive. So on the practical side, it's obviously useful. And here I think you can understand something about low-level processing. And it says also something about the relation between scene statistics and vision here. So this is the pipeline that I want to describe here. So in the first step, I will talk about filtering, and then I talk about thresholding, and then I talk about finding critical points here. And the first part here with the filtering in theory corresponds to group representations. Thresholding is linked to extreme value statistics, and then the critical points here are related to information geometry. I don't want to say so much about filtering and representation theory, but you can think of this as a generalization of a Fourier transform on arbitrary groups. And most images are defined on square grids. Sometimes you have hexagons, but almost all of them are nowadays on square grids. And the symmetry group of the square here is a group that is called the dihedral group with 4 elements, and it consists of 4 rotations and 4 rotations plus reflection. So in the case where you look at 5 by 5 pixels here, then this theory here tells you that you have to split up this 5 by 5 array here into different so-called orbits that are linked by these transformations here. And so every color here represents one of these orbits. And then the theory also tells you that the simplest or one of the filter of a pair that you should use on these orbits here are this simple filter currents -1, -1, 1, 1, -1, -1, 1, 1. So the theory tells you that this is the way you should do it. And it's very simple because you only do the subtraction and additions here. These filter systems have some nice properties. For example, the magnitude of the filter vectors is independent of these D4 transformations. And you can also show that if all these transformations on average appear equally often, then you have something that you can call group stationarity, and then these filters here define principal component analysis because these filter subspaces are invariant under all the transformations here. So, and that is true for very many natural image sources. So this was the first package here. So representation theory is the foundation, independence here. Then you have this optimal L2 error criterion, and then efficiently and easily to compute. So now we come to the next step, the thresholding and the extreme value theory. Because the common knowledge in image processing is that if you have this type of filtering, then you are not interested in all the garbage that has low values, but you look at points and regions where you have a large filter response. These are important. And in extreme value theory, you have one theorem that tells you that if you have a sequence of such stochastic variables and you take the maximum of these, then the theorem says that if you can normalize this new sequence here somehow, so that these new variables here converge to a non-trivial distribution, then this non-trivial distribution must be one of these extreme value distributions here. So it's a type of limit theorem like the normal distributions where you replace the sum with the maximum here. So this tells you that if you look at the maximum of these filter response results here, then if you can normalize it somehow, then they will converge to one of these GEVs. So that's the first step. The next step is another theorem in extreme value statistics. And that theorem tells you that if the stochastic variable x follows one of these extreme value distributions, then the tail of this stochastic variable can be modeled by the generalized Pareto distribution. So we have now the step filtering, maximum, and then the tail. And the thing here is that these extreme value distributions and the Pareto distributions have 3 parameters. And in the case here, for the Pareto distributions, one of the parameters is the threshold. And the threshold you can forget because that is the same for everybody. So in practice, you have a 2-parameter distribution family. And this is the definition of the density of these Pareto distributions. And here you have 3 different examples. So the red one here is one where the shape parameter is minus 0.4. Then the black one is 0.1, and the blue one is k equal to 1. You see, when the shape parameter grows, then the tail becomes longer and longer. So this is one example. And this was the extreme value statistics. And apart from the foundation in this limit theorems, you also have one very practical advantage of doing this here, because the Pareto distribution tells you that you should only consider values over a relatively large threshold, which means that most of the garbage that you compute in the first step, you don't need to consider anyway. And so you only look at very high values over the threshold. So it's also more efficient computationally, because you can concentrate on the very important things here. So as a result here, you get for each image, for each focal position, you get an Pareto distribution, which means that in the case of the autofocus sequence here, you get a curve in the manifold of the Pareto distributions. And so now can we use this information here? And one idea is that you can look at the Fisher information matrix for these generalized Pareto distributions, and then you can try to find out how is the information in this information matrix related to autofocus. So the first thing is that you have to compute the elements in this 2x2 information matrix. You can do this, and these are the 3 elements here. And then I propose to take the inverse of the determinant of the Fisher matrix as a sharpness measure. And the thing here is that if you compute the inverse of the determinant, you get this factorization here, which means that you have a term here with the sigma squared, which is roughly similar to the variance. And then you have an multiplicative factor here that modifies the significance of this variance part here. So, which means that you get some type of extra information of the shape of the tail here that tells you on how reliable your variance is. And if you look at the picture here, how this function looks like here, so this is the modification here, you see that if the k grows here, then this factor becomes more and more bigger and bigger, which means in the long tail case, the variance becomes more and more amplified here. And you can also see that k equal to minus 0.5 is the left endpoint, because the determinant is only defined for k greater than minus 1/2. So this is the description of the pipeline. And now, okay, nice theory and nice general results, but does it work? I mean, if it doesn't fit, okay, then you have a problem. So I implemented this, and for the estimation of the Pareto parameters, I use maximum likelihood estimator routine that is in MATLAB there. So this is the reason why I choose microscopy images, because there is a database which is type of, I don't know if it's a standard, but anyway, it's really big. So you have 50,000 images. You have 384 cells. Each cell is measured at 2 positions, and every position has 2 different types of stainings. So in all, you have 2 times 768 sequences. And for each sequence, you have 34 images. The images are in 16-bit TIFF format, and there is a standard, the result where they use some laser focusing procedure to define what is the sharpness region that is acceptable for this system. So everything between 11 and 23 is acceptable as autofocus result. So that's the way how these sequences were produced. So first they get a focus result for these laser instruments, and then they take up and down. So this is the standard database. And this was an example. This was a really good and easy example to see where the focus is. But remember that the sequence here come from automatic microscopy systems. So nobody is looking at the sequences that it's recording. And so for some cases, you may have some real problem. So this is one of the sequences that also comes in there. So some of the sequences are really garbage. There was nothing there. And so here is an example of how does it fit, because that's the first step. Here I used an GeV fitting for the non-zero gradient magnitudes. You see that almost all results are very small here, and the fitting is, yeah, okay. If you do the thresholding here, so for example, if you take the quantile 0.75, and then you do the fitting here, and then you see this fitting here, which is very good. And I did some goodness of fit tests also, which means that if the content of the image is okay, and then also these fitting things are okay. So the distribution of the filter magnitude over a high threshold is really fitted by these Pareto distributions. And then you have one parameter that is you have to choose, and you can have several quantile-based thresholds. Here is 0.75, and then you have only 5% left over here in this case here. And in both of the cases, the fitting is good. So, does it work? Here is the distribution of the automated focus position that I found. So, in general, it's really good. Sometimes it doesn't work, and it's interesting to see why it doesn't work. So, for example, I had one strategy where I start with 1, and then I go and then I look for the first maximum in the sharpness function, and then I stop. And this is one of the cases where this one result here is wrong, because there was some artifact here around position 7, 8. But then the real focus position here was correct. But since I broke here, then it was wrong. This one here is also a typical example when it may go wrong. If you look at this sequence here, for example, then you see the cell is not located in one slice, but parts of the cells are in different positions. So the cell is lying like this and not like this. So you get here the highest contribution here just outside the interval. But that's probably okay. And then the sharpness value itself has also some information, because here you get a good maximum here. It's almost correct here. But if you compare this curve here with the other curve here from another cell, then you see the sharpness value here was relatively low. So in this case, where I detected a maximum at 25, the absolute value of the sharpness function tells you that probably this is not too reliable. So the correct was at 32 for the other cell here. So if we now have one parameter that we can tune, which is the quantile, then the problem is how can you choose a good quantile? That's a general problem for all these Pareto-based methods. So the theory tells you you should use a high threshold so that the Pareto assumption is true. But if you have too high a threshold, then you have only a few samples. So there is somewhere a compromise. And then you see here, for example, if the quantile is 0.85, then 28 samples from this staining here was wrong. And this is the case because these stainings here are of this blurred type that I showed as a negative example. If you have this staining here, you have a much more detailed image structure in general, and then only 13 of these sequences were misclassified at the wrong position. So 1% here and 3% here. So conclusion, the filtering has a background in representation theory. The statistics come in the maximum selection here, and extreme value statistics is applicable. And then the curve in the manifold can be analyzed with information geometry. And the comment here I have, if I'm really satisfied with this method, is theoretically I'm satisfied because I understood a little bit more about the sharpness function. I found that it works. The problem is only that it is not very fast. And the critical point here is the parameter estimation of the Pareto distribution, which means that this is an optimization process, and I didn't spend too much time on optimizing the optimization. So there may be faster methods there, But for example, methods that depend on moments, for example, you cannot use them in general because some of these distributions that turn up have no moments. So probably someone in statistics has solved the problem. But anyway, so my conclusion is that theoretically it was interesting, and there is this crucial step of fitting the Pareto distribution to make it really useful. Thank you.